Hello guys, welcome to my channel Placement Bacha, and today we are going to solve the question validate the binary search tree. So here the concept is simple. They are going to give a tree and we have to return true if the given tree is a binary search tree, or we have to return false if our tree is not a binary search tree. First, let us understand what the binary search tree is. So binary search tree is nothing but, suppose here the root node is 15, all the elements which are present in the left subtree are less than 15, and all the elements which are present in the right subtree of 15 must be greater than 15, and no duplicate elements must be present. So here 15 is present and the next element, that is the left child, should be less than 15. Let us take it as 11. So and the left child of the 11 must be less than 11. So let it be 5. And the right child of 11 must be greater than 11, but it must be less than 15 as a whole. So let us consider that it is 13. And all the elements which are present in the right subtree should be greater than 15. Let us say it is 20, and the right child, okay, so can be anything like 22, so it must be greater than 20, and here it must be less than 20 and greater than 15 as a whole. Let us consider it to be 16. In order to validate the thing, that means validate whether the binary search tree is correct or not, okay, so we have two methods. The first method is, first we will perform the in-order traversal, and okay, if we perform the in-order traversal of the binary search tree, we are going to get an ascending ordered list. We will check, okay, whether our list is whether our vector is ascending ordered or not. If it is ascending ordered, okay, then we will return true. If it is not, we will return false. The second method is the recursive approach, and I am going to tell the recursive approach and the first method. So please watch the in-order traversal lecture, that is in-order traversal video, and use the recursive method, which is quite easier in order to find the in-order traversal vector, and just use the for loop and check whether v of I and v of I is less than v of I plus 1. If the v of I is greater than or equal to v of I plus 1, then return false. That's it. I am going to discuss the second method now. Okay. So the basic concept behind this recursive method is, so first I will be present on the root node, that is 15, and I am going to check. Okay, so there will be three parameters in my function. So first is the root node, and next is the max value, okay, max value, and next is the min value. So here I am going to check whether my roots value is greater than or equal to the maximum value. So this particular condition is applicable for the left subtree. That means, suppose if my root is present here and the maximum value in this instant is 15, so that means for this left subtree the maximum value will be 15. So here I am going to check whether my 11 is greater than or equal to 15. If it is greater than or equal to 15, then it's the that means it's the failure of the binary search tree condition. That means all the elements which are present to the left subtree must be less than the parent value. But in this case, but in this particular case, suppose if the element which is pointed by this particular pointer is greater than 15, that means the max will be 15, then this particular binary search tree is proven to be a non-binary search tree. And suppose if the roots value is less than or equal to the minimum value, and this condition is applicable for the right subtree, and here the 15 is going to act as the minimum value, and all the elements in this particular right subtree must have the value which must be greater than greater than the parent's value. that means if I, okay, in a particular instant, if my pointer is pointing on 20, that means if my root is pointing on 20, then all the elements which are present in the right subtree of this 20 should have the value greater than 20. It is cleared. And in the same way, if my parent is 11, all the elements which are present to the left subtree must have a value less than 11. So this is the condition what we must check, and we should validate. Okay, so if the left subtree and the right subtree holds this condition, and also the entire subtree holds this condition. So first let us code for this. So it is the inbuilt function what the lead code has given, so we will create our own function. So I'm going to return, okay, return the true or false by calling a function named as solve, and in this I'm going to pass the root node, and okay, let us say I'm going to take long max as my maximum value and long min as my minimum value. So because in this question they have given that 2 to the power of 31 is our value, if the range is around 2 to the power of 31, then in that particular case long data structure, that means long data type will be valid, because the data type is around 2 to the power of 12. So hence we have to take the long, that is 2 to the, which will have the range up to 2 to the power of 31. So now let us create that function. So bool solve, and here I'll pass the root as the parameter, and long max as the second parameter, and long min as the third parameter. I have said, so if root is equivalent to null, that means no element is present in the tree, then I am going to return true, assuming that they have given the condition if root is null, then the tree is binary search tree. Then I am going to check for the condition, that is if my root's value is greater than or equal to the max value, that means it is applicable for the left subtree. I am going to return false here. In the same way, if my root's value is less than or equal to the min's value, it is applicable to the right subtree, then again I am going to return false here, and then I am going to create a variable called as left subtree, and I am going to call the solve function recursively, and I am going to check whether my roots whether my left subtree of the root is a binary search tree itself. That means the subtree is itself a binary tree. That means we are breaking the entire tree into smaller subtrees, and we will check whether that subtree is a binary search tree. So then I have to pass the root's value itself as the maximum value for the left subtree, which I have explained here. So this 15 is going to be the maximum value for this left subtree, and then min will remain as it is. And I'll check for the right subtree also. I'm going to call the solve function recursively. I'm going to let us check for the right subtree, and max will remain as such, and the minimum value itself will be the root's value. So here 15 is going to act as the minimum value for this right subtree. Okay, and I am going to return left subtree, so which is a bool, and right subtree. So first, as it is a boolean data structure, either this left subtree will hold the value to be true or false, and this right subtree is also a bool. It is going to hold whether true or false. If both the left subtree and the right subtree holds true, then it suggests us that our left subtree is also a binary tree and the right subtree is also a binary tree. Hence our entire, and we recursively found whether our left subtree is a binary tree or the right subtree is a binary tree for each and every subtrees, and as a whole we are finding whether our binary search tree is a, or whether the given tree is a binary search tree or not using these conditions. So I think this code must work fine. Let us run the code. Yeah, it's working fine. So, and let us check for the second condition. That means the second example. Yeah, it's working fine. So now let us submit the solution. Yeah, it has accepted our solution, and 98.96% my solution is faster, and in terms of space complexity it is 89.68% faster. So it's a good solution. So thanks a lot. So this is about how to validate the binary search tree. The basic funda is that, so we will be given a binary tree, so you can do the in order traversal and you can check whether the in order traversal is in ascending order or not. So this is the easiest method. If you want to use the recursive method, then what you have to do, so first you have to find, okay, so whether the current root value, that means initially we were present at the root, and we will take that root as the maximum value for the left subtree, and the particular root's value, that means the initial root which was present, its value act as the minimum value for the right subtree, and then we will check if the root's value, that means the root's left child's value is greater than or equal to the maximum value. If it is greater than or equal to the maximum value, we will return false, as the left subtree must be lesser than the max, and we are going to check whether our root's value is less than or equal to the min. So here min is nothing but the parent's value, so all the right childs must have a value greater than the parent's value. We will check the negative condition, that is the opposite condition. If it is less than or equal to minimum value, if it is less than or equal to minimum value, it it makes the binary search tree condition to be false, so hence we return false. So I am going to check recursively for the left subtree and the right subtree. So that means we are going to break the entire tree into subtrees, and we will check whether each subtree is a binary search tree or not as a whole after finding recursively. So we will see as a whole whether the tree is binary search tree or not, and then we'll submit the solution. So don't forget to subscribe. Thank you guys.